Okay, so there's a section in the first chapter of the book that maybe doesn't fit all that great in here, but I'm going to go over it right now anyway. Um, and that involves a situation where two objects are dependent, their motions are dependent upon one another in a very direct way. And in this case, this is usually the typical examples and stuff are where we have all these pulleys and some arrangement of pulleys and a cable connecting the two. Perhaps we could have a different arrangement with multiple cables and stuff. But um, the really, the only trick to this is to determine exactly how the motion of, say, block B is related to block A in this instance. And it has to do with the length of the cable being a constant, right? I mean, unless the cable is stretching or something like that, which is usually ignored, um, you have a situation where the motion of B is directly connected to the motion of A. And in this particular example, you can kind of see what's going on here. We have block B being pulled down under gravity, and as a consequence, block A, you know, will be pulled along in that direction. All right. So uh, in these sorts of situations, first thing you can kind of do is write a relationship for the length of the cable as a function of the parameters that are given to you or parameters that you can make up, right? So let's use, so here is the anchor, here's an anchor point for the main cable that sort of snakes around that way. And we can use this as a datum. This is also another fixed point. This pulley here is anchored up here, so we'd establish this point as sort of as the datum with which we're going to measure the motion of block B. And this point, this pulley here is rigidly connected to block B, so we can measure this to be the distance. All right, so the length of the cable, we'll call it little l. Let's just go from this side. We're going to use this point here as our datum, so we got to go down SB. It's called SB because if you can, as you can tell, this distance as it changes is directly related to how B moves. All right, so the distance that B travels is, I could also measure it by measuring the change in this distance here. Okay, so we have SB, and then I'll call this, maybe I'll call this L1 across the the distance from here to here, from the two tangent points of the cable. This distance will never change, so it's going to wind up being ignored, but just for completeness I'm going to put it on there. And then we go up another SB, so we have okay, so now we're here, and then we got to traverse around this second pulley, you know, from this point to this point. We'll call that L2. Okay, and then we have this long length here. We're calling that H. And then we have this quarter turn around this smaller pulley, which is L3. And then finally SA. Okay. So the parameters that we're interested in are SB and SA, right? We're actually interested in the motion of the two masses here. So we can combine everything else. Let's combine, and they're all constant. So L1, L2, H, and L3 are all constant. So we're going to call that, maybe we'll call that we'll give that the letter big L, I guess, and we'll call that L1 plus L2 plus L3 plus H. That's just so we don't have to write all this stuff over and over again. So L, I got 2 SBs, an SA, and then I got L. So this actually tells you exactly how the position of B is related to the position of A. If this is well, it starts to tell you anyway. You can start seeing some insight that what's going to wind out. This is constant and this is constant, so 2SB plus SA is going to equal a constant. And so you can kind of see initially that if I change SA, SB is going to change by half as much and in the opposite direction. You can kind of tell that just by looking at it. But for completeness sake, we're going to take the time derivative. So just doesn't matter. This is a constant, so that's going to be equal to 0. And so what's the derivative of SB? That's just going to be the velocity or the speed. So 2VB plus VA equals 0. Or, and then likewise for the acceleration, we just take the time derivative of this again. And that's pretty straightforward. We just get 2 times the acceleration of B plus the acceleration of A equals 0. Okay, so that's how these 2 points are, that's how the motion of these 2 objects are connected in this particular arrangement. So just to discuss this a little bit, so there's some stuff we did that was implied right off the bat that sort of set up our problem for us, right? We chose coordinate systems. We chose a coordinate system. So we chose this to be the origin for block B, and that this variable SB describes its motion. Its motion is only in one dimension, so we can describe it with one number. All right, and we chose SA to be measured from this point to here. But those choices are somewhat arbitrary. We could just as easily, we just need a fixed point with which to measure the motion. So we could have chosen this point to also be the origin for the motion of block B as well, and we would get a different set of equations, but ultimately the answer would be the same. So let's just, for instance, take, so SB is positive as B descends, so increases as B descends. But if we were using this, it would decrease as B descends, so you would wind up getting a negative sign here. And we're going to go over several examples to we're going to do a lot of these examples. It ought to become clear, but I just want to point out that there's some arbitrariness in the way that we set it up, but ultimately you should get the same answer. And then we can look at this and verify that it makes sense. All right, so SB is increasing, SA is decreasing the way we have it set up. So they should be related negatively, right? If we flip that around, SB would be decreasing as well as SA would be decreasing. So then you'd get a positive value here. They'd be positively related like that. I don't know. Hopefully the examples we're going to be going over will make it pretty clear.